we're going to go through Pset 1 solutions. So, what are the criteria for Bragg diffraction? So, we need to have a regularly spaced array of obstacles or particles. So, again, regular, basically an ordered array of obstacles, or just some obstacles that have some periodic or, even some spacing. So, just a regular array of obstacles or particles. So, that's our first criterion. So, we need to have some type of array, and we're drawing a metal lattice here. We could have a glass or a polymer or something amorphous as well, but just some regular array of obstacles or particles. That is the first criteria. The second criteria is that we need to make sure that our incoming wavelength, lambda, is on the order of the distance between these particles, d here. So typically with X-ray diffraction, we are going to use copper alpha radiation. So copper alpha radiation, which is 1.54 angstroms. And that is on the order of the distance between atoms in a lattice. So on that order, again, we need to make sure that this is on the order of this distance, not too much larger, else we miss it. Too much smaller, we won't kind of be able to, basically see that peak as well. Excellent. So regular array of spaced obstacles or particles is our first condition. Second condition, lambda must be on the order of this the distance. Excellent. So when we see a peak in intensity, is that constructive or destructive interference? So that is constructive interference. So remember, we need the two waves to be kind of in phase, and that is how we were able to kind of derive Bragg's diffraction. So actually, let's go through our notes right here. This is just kind of recapping what we were talking about in the notes. But as we saw in the notes for Bragg diffraction, we need to make sure when this kind of wavelength bounces off, these two waves need to be in phase. So this extra distance traveled, AB plus BC, must be n, which is an integer number, times the wavelength. So with that kind of simple geometry and figuring out sine and theta and Bragg angles, we're able to kind of derive Bragg's law here, which is n lambda equals 2 dhkl sine theta b. So very similar to kind of what we were talking about in our class. So excellent. So that's pretty much all that is there. So constructive interference, number 1 is done. List 3 type of intramolecular interactions. So intra, so those can be metallic, those can be ionic, those can also be covalent. And remember, these are all above essentially a KT. So if we go again back into our lecture notes, if we look at some intramolecular interactions, so for example, actually not here. So if we look for some intramolecular interactions, oops, where are we at? Let's keep going down a little bit. So these are all our intramolecular interactions. So covalent, 200 KT, ionic, 80 KT, metallic, 20 KT. For intermolecular, we have van der Waals interactions, we have H bonds, we have dipole-dipole, we have polar interactions, we've got steric interactions, we've got quite a few different types of intermolecular interactions. So I'm just going to list the H bonds, we have dipole-dipole, we have van der Waals, we have steric, you could have coulombic, lots of different interactions, little ion-ion interactions, but anyways. So, excellent. Which types of interactions have energies greater than KT? That would be our greater than KT are intramolecular, less than KT is intermolecular. So intermolecular is less than 1 KT. And what that means is that those bonds can be basically broken and reformed at room temperature. Fantastic. So we discussed a couple different potentials in class, one of them ubiquitous being the Leonard-Jones potential. So let's go ahead and look at our Leonard-Jones potential. It should be around here. So let's go ahead and define it in Mathematica. Got this up here. So my Leonard-Jones potential is equal to my 4 times epsilon times sigma divided by r to the 12th minus sigma, oops, let me make sure to put it to the power, sigma divided by r to the 6th power, not 4, r. Great. And then in this problem, so that's our Leonard-Jones potential. In this problem, we are told that, let's go look down here. So we are told that epsilon equals 0.167 electron volts. Our sigma is equal to 2.314 times 10 to the minus 10 meters. So Jones potential. And we are asked to double check the results. These are supposed to be for copper. So we can look at the equilibrium distance for copper atoms. So equilibrium distance, we need to set our potential to equal 0, or the derivative. So take the derivative, we need to find, again, that minimum energy. So for our equilibrium distance, so we're taking the derivative, Leonard-Jones, with respect to R, and we are going to solve when does this set equal to 0 for R. So as we can see here, our equilibrium distance is 2.6 essentially angstroms. So that is our equilibrium distance. So let's just kind of put this here, equilibrium. So that is our equilibrium distance. The distance when the force is maximized, we know if we take a potential and we take, so if I want an energy, if I want to see when the force is maximized, so my force is going to be equal to minus the gradient of this. So that's my force. So when my force is maximized, is d of the force, set equal to r. This is also the inflection point, essentially, our change in curvature. So let's solve when the force is maximized here. And 2.88 times 10 to the minus 9. Great. So distance to force is maximized, we got it. And then copper stationary, the equilibrium distance should be just about 2r. So our equilibrium distance is 2r. If we look at copper, so let's look at our metallic radius right here. Copper, our metallic radius is about 1.28. So 1.28 times 2, 2.28 times 2, 2.56. So this is actually quite, it's a little close. So it's almost 2r, but not quite. So our equilibrium distance is not twice of this radius. So slightly off, but pretty close. So maybe, again, this is always a choose your own adventure answer. So fantastic. So still a little bit off. And again, what can explain the difference? The Leonard-Jones potential is not really, it's made for van der Waals interactions, not for metallic interactions. So that's kind of the little caveat there. What type of bonding does iron have? So we said, remember, anything here, we got metallic, germanium, that's always like a semi-metal, like are we metal or are we, not metal? But again, we could call it metallic bonding, or you could kind of make it covalent bonding. But you could say that that's also metallic as well. So metallic. NaCl or polyethylene. So polyethylene, we know it's this, H. So we know we have along our backbone, we have covalent. So our intramolecular interaction is covalent. So this is a covalent bond. Here, we've got van der Waals all over the place. So van der Waals. What about NaCl? So let's look at the difference. So remember, we said that if the electronegativity difference is greater than 1.7, then that is ionic bonding. So let's look at our electronegativity. So let's look. Electronegativity, again, is this second one right above the electron configuration. So Na has an electronegativity of, actually, sorry, that's the second one. So the one up of 1.91. So our Na is 0.93. And what's our chlorine? I believe it's 3.16. Yeah, 3.16. So 3.16 minus, let's look at 3.16 minus 0.93. What does that give us? Yep, that is an ionic interaction. So if it is greater than 1.7, it is ionic. So if our electronegativity difference is greater than 1.7, ionic. So our ionic here, let's look at polyethylene. We just said, again, we have covalent bonds, we have van der Waals interactions. Fantastic. And then now, let's go to our Al2O3. So let's look at Al2O3. So let's look at our Al. We're at 1.61, it looks like. Let me just erase here. 1.61. O is going to be 3.44. So 1.61, 3.44 minus 1.61. 1.83, also ionic. So again, that's just from our lecture notes, and we can kind of double check and look at that right here. Yeah, 1.7. So those are both ionic interactions. Fantastic. So I think that gives us this problem finished. State whether this is an isomer or a conformer in Figure 1, and if so, isomer, what type? Justify and explain. So remember, isomer is same kind of isomer is going to be the same chemical constituents, but a distinct structure. So that's kind of the key idea that we're looking for here. A conformer will be related by rotation. So if you look at here, we have C, C, O, O. You know, these are chemically identical, but they are not structurally distinct because we can rotate around this kind of bond here. So these can flip and rotate and kind of move around. So because there's a single bond here, they could rotate and move. So we are actually completely fine here. The next molecule here, you can see here again, chemically identical, but these are structurally distinct because we can't rotate around this double bond here. So this is an isomer. More specifically, it's a structural isomer. You could also call it a cis trans as well. But anyway, I'm sure that the people will say, no, you can't technically describe it as that, blah, 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 blah. Anyways, fantastic. So this one is done. NaCl crystal, cation and anion. So Na is our cation. It will be 1 plus. Cl will be -1. So these positives are always, again, our cation. These would be our anion. Again, so this will lose an electron. This will gain an electron. How about CaCl2? So Ca is going to be 2 plus. Cl is going to be 1 minus. What about UO2? So UO2, U is going to be 4 plus. O is going to be 2 minus. So that's it. So again, cation, cation, anion, 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 cation. So lose 2 electrons, lose 4 electrons, we're good to go. Excellent. So now it says in the following the directions, or draw the following directions with the don't follow the directions. We'll follow the directions and draw the following directions. But draw the following directions within the empty unit cell below in figure 2, 1, 1, 2, 0, -1, 1. All right, so let's do 1, 1, 2 first. So let's change colors here. I'm going to do 1, 1, 2. I believe that's what we were asked to do. So 1, 1, 2. So my trick when we're drawing these, so I need to end up, so I need to finish minus the start. So these need to be a half because I have a 2 here, but you'll kind of see this. So let's go ahead. So this needs to be a positive half. So this could be basically 1 half, a 1 half, and then this could be basically a 1 and a 0. So what is that going to leave me with? It's going to leave me with a half, and then 1, and that will leave me multiplying it out. So my finish is going to be 1, 1, 1. So that's going to be my arrow, and my start is just going to be right here. So there we go. So finish minus start. There we go. Let's look at the next one. I'm going to do green. So 0 minus 1, 1. So 0 minus 1. So here, again, my finish, I just need this finish minus my start. So I'm going to do just 1, 1. And then I need this to be basically a 0 and a 1. And then this needs to be a 1 and a 0. There it is. So my 1, 0, 1 will be right here. So this arrow. And then my 1, 1, 0 will be right here. So it'll be from here, here to here. And again, there's lots of different possible solutions to this particular problem. So don't think that you didn't get it correct necessarily. And then finally, 1, 2, 2, minus 2, minus 2. So 1, minus 2, minus 2. So similar to what we kind of saw before. So this needs to be a half. So I need to be, this is 1 minus a half. And then the rest of them just need to be 0, 0, 1, 1. Because then that will give me the rest of those values. So my finish is going to be here. And then my start will be a half and then 1. Oops, don't copy that. So a half, 1, 1. So from here to here. There we go. Those are my directions. Now we're supposed to draw the planes. So 2, 0, 1. So let's go ahead and restart this. So 2, 0, 1. So 2, 0, 1. So I know that these are my HKL indices, so that I know my intercept is a half, inverse of this. Y is going to be infinity, and my Z is 1. So if I intersect here, X equals 1/2. If I intersect Z at 1, so if I intersect Z right here, I can just going to draw this as so. A half, and we never intersect that way, we're good. Now I'm going to kind of erase here just to kind of give us a nice drawing here. And then let's look at our other one. 1 minus 2, 0. All right, so whenever you're dealing with a minus, so 1, 2 minus 0. So now we know again, x equals 1, y equals minus a half, and then z is equal to 0. So I need to go in the negative y direction. So I need to change my origin whenever there's a kind of a negative. So I am going to define my origin as follows. So I want to define my new origin right here. So this is my O prime. Because now this is my x, this is my y. So I'm going to intersect in my minus y here. I'm going to intersect in the positive 1 here. This is my x, this is my new y. And then I'm never going to intersect essentially the other axis. And you can kind of build it up and do the same thing here. So negative and then 1. So you can kind of draw. It looks a little bit disgusting, but that would work. So that's your 1 minus 2. Sorry, I changed colors there. So you can kind of draw it like this. So it's kind of hidden right in there. But anyways, so those are your solutions for that, for the planes. So directions, planes, you're all experts. We did this well in class. Oh, I like this one. What type of conventional unit cell? How many atoms? What's the atomic packing factor? So we know here that this is simple cubic. So that's 1 atom. This is BCC. This is 2 atoms, or actually 2 atoms right here. And this is FCC, and that's 4 atoms. We know that this, we can kind of go back through our notes, but this is not close packed. So my atomic packing factor is less than 0.74. Same thing for BCC, but for FCC, we are at 0.74. It is a close packed structure. So again, you'd have to kind of quantify it and calculate that out, but you can kind of give that value. And that's in the notes as well. Determine the directions in A. So let's go ahead and kind of write these out. So what's my finish? 1, 0, 1. What is my starting point? 0, 0, 1. So what's my direction? As we kind of might anticipate, 1, 0, 0. There we go. What about this direction over here? My finish is 0, 1, 0 minus my start, which is 0, 1, 1. So what is my ending direction? 0, 0, 1 half. What about this guy? This is going to be, my ending point is 1, 1, 0 minus my origin. So there it is. And then finally over here, let's kind of, my finishing point is a half, 0 minus my start, which is again 0, 1, 1. So let's go bring that down. So I'm left with a half, and then we are at a half hat, and then we are left at basically 1 hat. So we are left with basically 1 hat, 2 hat. There we go. So that is our solution. So we are good to go there. So those are the directions in A. What about the planes in B and C? I'm going to kind of erase here. So the planes, the close packed planes in B, actually, well, let's look at the planes in B. So in B, I only intercept Z at a half, so that is going to be 0, 0, 2. So, because again, my Z is equal to 1 half intercept, and my L, HKL, is going to be over Z. What about here? Again, I intersect the origin. I need to redefine my origin. So if I draw that here, this is my new X, this is my new Y. So my X-intercept is equal to -1. My Y is equal to basically infinity. And then my Z is equal to 1. So my 1 hat, 0, 1. There we go. What are the close packed planes for? So again, no close packed structure, no close packed plane, no close packed plane, and then this is 1, 1. So no close packed planes if there's no close packed structures. But there can be close packed directions. My close packed directions for simple cubic, 1, 0, 0. For BCC, it is going to be, draw this 1. And then for here, this my close packed directions will be 1, 1, 0. The family. Great. Calculate the planar density for the plane in C. And also, what is the atomic packing factor for A? Is a close packed structure. So planar density for C. So let's go ahead and calculate that out. So if I draw this, I have atoms like here. So what is my planar density equation? What's my number of atoms? Quarter, 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 half, half. So 2 times pi r squared. what is the distance here? This is A. This is times A square root of 2. And we also know that for A, for an FCC structure, A is equal to 2 times square root of 2r. So if I have 2 times pi times r squared, oops, I divide that by A times square root 2. Is this close packed? We need the number to be 0.9069. Nope. And this is correct because there's no close packed. That is not our close packed plane. So that's always a good check. What about the, so it is not close packed, as we might expect. Atomic packing factor for A, is it a close packed structure? So we know for simple cubic it is not a close packed structure, but let's go ahead and look at it. So for atomic packing factor, 1 times the volume of a sphere, so 4/3 times pi times r cubed. I know you're probably cringing at my parentheses, but don't worry about it. And then my A, so let's say I'm going to redefine my A. This is dangerous, don't do this. But my A is equal to 2 times r for a simple cubic structure. So A cubed, what do you know? And it is less. So we're good to go. Fantastic, we're almost there. I had my undergraduate researcher examine 3 materials: metal, random coil polymer, gas. Gave me 2 for reference, didn't label correctly, so we know that this is gas, this is a metal. Again, sharp peaks, long periodic order, infinity, and this is going to be basically, it's going to be a polymer, or liquid crystal, or any really amorphous material. Fantastic. And then finally, I'm interviewing at Vandelay Industries. They give me the following RDF PDF. Is this a metal, polymer, liquid, or gas? So we know, based on this, it is definitely for sure a metal. So what do the other 2 materials look like? We've already answered that question above here. So we can draw that and just show that there. What specific element of material is represented by the PDF? This material has 12 nearest neighbors. So basically, we know that if it has 12 nearest neighbors, that means that the integral of this peak is going to be equal to 12. So if we have 12 nearest neighbors, we know that the material that we're looking at is a metal, and it's also FCC. So if it's FCC, we know that this is equal to 2r, and that this distance is our next nearest neighbor distance, which is 2r square root of 2 for a FCC material. So I can go ahead and solve for r. So 3.53 angstroms, so that equal to 2 times r times square root of 2. Solve for r. That's going to give me 1.248. So my r is equal to this. So my 2r, which is on the other information here, so 2 times r, will be that. So 2.5-ish. So let's go ahead and look at an FCC structure with a metallic radius of 1.25. So we need FCC, so we need this little dot here. So if I look at my structures, oh, metallic radius is the first one. Look at nickel. My nickel here, metallic radius of 1.25, FCC, we got it. That's it. So that's how you kind of answer some of these solutions. If it's a different material, we know that for BCC, this would be 4r over square root of 3. We know that for also, if this was simple cubic, we would also know it would be 2r square root of 2. But we would know then this would be, the integral would be 6. For BCC, this must be 8. So nearest neighbors. So remember, integral gives us the nearest number of nearest neighbors, and then these x-axis gives us the nearest neighbor distance, which is always equal to 2r, and the next nearest neighbor distance will change depending on the metal. So good luck with that question on your exam. Thanks. I hope this was helpful, and yeah, I'll see you all next time. Thanks. Bye.